Welcome my dear learners for this course on design of machine elements 1. So far we have started discussion on design of machine elements. In this course on design of machine elements 1 we have discussed about principal stresses and also we have solved numerical problems on principal stresses. Moving ahead in today's lecture, let us discuss theories of failure. What is this theories of failure? Why it is important in mechanical engineering is the question to be answered first. If a specimen is loaded in one type of loading, that is purely axial tension or compression or pure bending or pure torsion, then it is easy to predict when the material is going to fail. But if the combination of load is acting on the specimen, that is combined axial and bending, combined bending and torsion, combined axial and torsion, it is very difficult to predict when the material is going to fail. In order to predict the likely way of failure of the material or when the material is going to fail, the theories of failure has been formulated. There are many theories of failure, but the most popularly used three theories of failure is what we are going to address in today's lecture or in this course on design of machine elements 1. The very first theory is maximum normal stress theory or Rankine's theory. The very first theory is maximum normal stress theory, or it is called as Rankine's theory. According to maximum normal stress theory or Rankine's theory, the failure of a specimen takes place if the maximum principal stress at any point in the specimen exceeds the yield or ultimate stress. According to maximum normal stress theory, the failure of a specimen takes place if the maximum principal stress at any point in the specimen exceeds the ultimate or yield stress. If there are three principal stresses acting on the three mutually perpendicular planes on a specimen or a material such a way that sigma 1 is greater than sigma 2, which is greater than sigma 3, where sigma 1, sigma 2, sigma 3 are principal stresses acting in three mutually perpendicular planes. What is principal stress? We have discussed in our previous lecture itself. The plane on which only normal stresses act with zero shear stress is termed as principal planes. The stresses acting on principal planes are termed as principal stresses. So if the maximum principal stress at any point in the specimen exceeds the yield or ultimate stress, then the specimen will fail according to normal stress theory or Rankine's theory. If this is the condition, we have the three mutually perpendicular principal stresses such a way that sigma 1 is greater than sigma 2, which is greater than sigma 3, then according to this theory, sigma 1 should be less than or equal to sigma yield by factor of safety. Sigma 1 should be less than or equal to sigma yield by factor of safety. This theory accounts for maximum principal stresses and neglects the shear stress, ignores the shear stress. Hence this theory is mainly employed for brittle materials. This theory is mainly employed for brittle materials, where the mode of failure for brittle materials is through fracture. These brittle materials will never yield, they will fail through fracture. Next, coming for the second important theory is maximum shear stress theory. Maximum shear stress theory or maximum shear stress theory, or it is also called as Guest's theory. Guest is the scientist name who developed this theory of failure for combined loading cases in order to predict the likely mode of failure of a specimen, or when the material is going to fail when it is subjected for combined loading case. Now according to maximum shear stress theory, the failure of a specimen takes place if the induced shear stress exceeds the maximum allowable shear stress in the specimen or shear stress in yielding. According to maximum shear stress theory, the failure of a specimen takes place if the induced shear stress exceeds the shear stress at yield point. So therefore, according to this theory, if I convert the statement into equation, the maximum induced shear stress should be always less than or equal to yield stress in shear yield stress, or shear stress at yield point divided by factor of safety for safe design. Now we know that tau yield is equal to sigma yield by 2. It is half of sigma yield. So therefore, according to this theory, tau max should be always less than or equal to sigma yield by 2 times factor of safety, where tau max is nothing but max of sigma 1 by 2 or sigma 2 by 2 or sigma 3 by 2 or sigma 1 minus sigma 2 by 2 or sigma 2 minus sigma 3 by 2 or sigma 1 minus sigma 3 by 2. We should choose maximum of this and take it as the tau max. So once you get tau max, we can find the factor of safety. So this is how the maximum shear stress theory is employed in designing of ductile materials. This is suitable for ductile materials because this theory is based on yielding. This theory is based on yielding, where the failure of a specimen is by yielding, whereas for brittle materials the failure of a specimen is by fracture. Next, one more important theory is there, that is distortion energy theory, or it is Henke-Misses theory. Henke-Misses theory, or it is also called as Henke-Misses theory or distortion energy theory. This is the third very important theory which is employed for analysis of ductile material. What does this distortion energy theory states is that the strain energy of distortion per unit volume in the specimen equals or exceeds strain energy of distortion per unit volume of a standard tensile test specimen when yielding begins will cause failure of the specimen. So according to this theory, the formula for design is given by sigma yield by factor of safety whole square is equal to sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 1 sigma 3, where sigma 1 sigma 2 sigma 3 are magnitude of principal stresses acting in 3 mutually perpendicular planes. So these three are the most important theories of failure. Apart from the other theories like Hike's theory, the criteria for failure can be referred to our design data handbook written by K. Madhavan and K. Balavir Reddy. We are referring 4th edition. If you look at equation 2.8 onwards, you have formulas for theories of failure, where the value of sigma yield by n is termed as sigma E, which is called as allowable stress, Kindly make a note of this. Is called as allowable stress. Apart from that, if the principal stresses are not specified directly, we should find the principal stresses. How to find the principal stresses? We have solved a numerical problem in our previous lecture itself. When we have normal stresses on x and y direction and a shear stress acting on xy plane, we have formulas to find maximum principal stress and minimum principal stress and maximum shear stress. Using maximum and minimum principal stresses, we can employ the formula and design and also detect likely mode of failure of a specimen in combined loading case using theories of failure. With this very brief introduction to theories of failure, let us quickly solve problem number 1 of our discussion on theories of failure in today's lecture. Let me pause this video for a while so that you people can copy it down. Later we will address problem number 1. Now moving ahead, the problem number 1 states that a material has a maximum yield strength in tension and compression of sigma yield is equal to 100 megapascal. Compute the factor of safety for the following theories of failure using the following stresses: maximum normal stress theory, maximum shear stress theory, distortion energy theory. Sigma 1, for case A, sigma 1 is 70 megapascal, sigma 2 is 70 megapascal, sigma 3 is 0. For case B, sigma 1 is 70 megapascal, sigma 2 is 30 megapascal, sigma 3 is 0. For case C, sigma 1 is 0 megapascal, sigma 2 is minus 30 megapascal, and sigma 3 is minus 70 megapascal. Let us solve this problem. If I move for solution, first let me take Rankine's theory, that is maximum normal stress theory. Maximum normal stress theory. Just now we have discussed, according to maximum normal stress theory, sigma max should be less than or equal to sigma yield by factor of safety, where sigma max is what? Max of sigma 1 comma sigma 2 comma sigma 3. Now if I take case A, sigma max of sigma 1 comma sigma 2 comma sigma 3 is 70 megapascal. So therefore sigma max equals sigma 1, which is equal to sigma 2, which is equal to 70 MPa. So therefore, according to this theory, sigma 1 should be equal to sigma yield by n. Hence n is equal to 100 divided by 70, which is nothing but 100 by 70, which is equal to 1.43. Next, if I go for B, sigma max is max of sigma 1, sigma 2, sigma 3. So maximum is again 70, that is sigma 1. Sigma max is equal to sigma 1, which is equal to 70 megapascals. So therefore sigma 1 should be equal to sigma yield by n. Hence n is equal to 100 by 70, which is again equal to 1.43. Next, if I go for case C, max is minus 70, which is compression. I should take magnitudinally, numerically maximum value. The sign indicates whether it is tensile or compression. Keep that in mind. So here the maximum is again 70 MPa, but it is compression. Keep that in mind. So therefore here also, according to this theory, sigma 3 should be equal to sigma y by n. Hence n is equal to 100 by 70, which is equal to 1.43 once again. So therefore for all the three cases, the factor of safety is found to be 1.43. Next, moving ahead for second theory, that is maximum shear stress theory. Maximum shear stress theory. According to this theory, failure will take place if tau max equals or exceeds tau yield by factor of safety, right? Where tau yield is equal to sigma yield by 2, hence it is tau max is equal to sigma yield by 2n. What is the value of tau max? Tau max is max of sigma 1 by 2 or sigma 2 by 2 or sigma 3 by 2 or sigma 1 minus sigma 2 by 2 or sigma 1 minus sigma 3 by 2 or sigma 2 minus sigma 3 by 2. So according to this, what is the maximum value we have for case A? For case A, if I consider, the maximum value will be sigma 1 by 2, right? The maximum value will be sigma 1 by 2 or sigma 2 by 2. So for case A, tau max is sigma 1 by 2 which is equal to sigma 2 by 2 which is equal to 70 by 2 which is equal to 35 megapascals. Hence we will have tau max should be equal to sigma y by 2n. So 35 is equal to 100 by 2n. So n will be equal to 1.43 again, because 35 into 2 is again 70. 100 by 70 is 1.43. Moving ahead for case B. Here also sigma 1 by 2 is greater, so therefore tau max is sigma 1 by 2, hence which is equal to 35 MPa. Therefore tau max should be equal to sigma yield by 2n. Again 35 is equal to 100 by 2n. Here also n will become 1.43 only. Next, if I go for case C, there the tau max will be sigma 1 minus sigma 3 by 2 which is 0 plus 70 by 2 which is equal to 35 MPa. Therefore here also the value of n will become 1.43. So for all the cases, according to maximum shear stress theory, again the factor of safety is 1.43 itself. Moving ahead for the final one, that is distortion energy theory. That is distortion energy theory. According to distortion energy theory, we know that criteria for failure is sigma yield by n whole square is equal to sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 1 sigma 3. So if I go for case A, it is 100 by n whole square is equal to 70 square plus 70 square, sigma 3 is 0 minus 70 into 70, remaining 2 are 0. So therefore n will be equal to 100 square divided by 70 square plus 70 square minus 70 into 70, root of answer. It is 1.43 again. It is 1.43 again. Next, go for case B. For case B, it is 100 by n whole square is equal to 70 square plus 30 square minus 70 into 30, because sigma 3 is 0 there also. So n will be 100 square divided by 70 square plus 30 square minus 70 into 30, root of answer. It is 1.64. The answer has been changed. It is 1.644. 1.644. Go for case C. For case C, it is 100 by n whole square is equal to minus 30 square plus of minus 70 square minus 30 into minus 70. How much is the factor of safety? 100 square divided by 30 square plus 70 square, 30 square plus 70 square, minus of minus is plus, so minus 30 into 70, root of answer. Again it is 1.644. 1.644. So this is how you should solve problems on theories of failure when you know maximum principal stresses or principal stresses in three mutually perpendicular planes. If you have biaxial stresses, maximum and minimum principal stress are given like case B and case A, you have only two values, sigma 3 is 0. Then automatically sigma 3 will get eliminated, put sigma 3 as 0 and solve. This is how you should solve when you know principal stresses. If principal stresses are not given, you people should determine the principal stresses like what we have done in our previous lecture. I will take such problems in our next lecture and try to conclude theories of failure in our next lecture. That's all from today's lecture. Thank you all.